In the name of Almighty God, I'm Mahsa Sankoshi, and today I want to talk about hidden Markov model exploration. Firstly, I want to talk about Markov model. In probability theory, a Markov model is a stochastic model used to model pseudo-randomly changing system. It is assumed that future states depend only on the current states, not on the events that occurred before it. That is, it assumes the Markov property. Generally, this assumption enables reasoning and computation with the model that would otherwise be intractable. For this reason, in the field of predictive modeling and probabilistic forecasting, it is desirable for a given model to exhibit the Markov property. And what about the Markov model introduction? Andrei Andreevich Markov, 14 June 1856 till 20 of July 1922, was a Russian mathematician best known for his work on stochastic processes. A primary subject of his research later became known as the Markov chain. There are four common Markov models used in different situations depending on whether every sequential state is observable or not, and whether the system is to be adjusted on the basis of observations model. For example, the Markov models, we have a two-section system is autonomous, a system is controlled. In a system is autonomous, the feature of system state is fully observed. We can use Markov chain, and system state is partially observable. We can use hidden Markov model. And if the system is controlled, for system state is full observable, we can use Markov decision process. And if the system state is partially observable, we can use partially observable Markov decision processes. And what about the Markov chain? The simplest Markov model is the Markov chain. It models the state of a system with a random variable that changes through time. In this context, the Markov property indicates that the distribution for this variable depends only on the distribution of a previous state. An example use of a Markov chain is Markov chain Monte Carlo, which uses the Markov property to prove that a particular method for performing a random walk will sample from the joint distribution. And what about the hidden Markov model? A hidden Markov model is a Markov chain for which the state is only partially observable or noisily observable. In other words, observations are related to the state of the system, but they are typically insufficient to precisely determine the state. Several well-known algorithms for hidden Markov models exist. For example, given a sequence of observation, the Viterbi algorithm will compute the most likely corresponding sequence of states. The forward algorithm will compute the probability of the sequence of the observations, and the Baum-Welch algorithm will estimate the starting probabilistic, the transition function, and the observation function of a hidden Markov model. One common use is for speech recognition, where the observed data is a speech audio waveform and the hidden state is the spoken text. In this example, the Viterbi algorithm finds the most likely sequence of spoken words given the speech audio. And what about the Markov decision process? A Markov decision process is a Markov chain which state transitions depend on the current state and an action vector that is applied to the system. Typically, a Markov decision process is used to compute a policy of actions that will maximize some utility with respect to expected rewards. And what about the partially observed Markov decision process? A partially observable Markov decision process, or POMDP, is a Markov decision process in which the state of the system is only partially observed. And POMDPs are known to be NP complete, but recent approximation techniques have made them useful for a variety of applications, such as controlling simple agents or robots. And what about the Markov random field? A Markov random field or Markov network may be considered to be a generalization of a Markov chain in multiple dimensions. In a Markov chain, state depends only on previous state in time, whereas in a Markov random field, each state depends on its neighbors in any of multiple directions. A Markov random field may be visualized as a field or graph of random variables, where the distribution of each random variable depends on the neighboring variables with which it is connected. More specifically, the joint distribution for any random variable in the graph can be computed as the product of the click potentials of all clicks in the graph that contains that random variable. Modeling a problem as a Markov random field is useful because it implies that the joint distributions at each vertex in the graph may be computed in this manner. And what about the hierarchical Markov models? Hierarchical Markov models can be applied to categorize human behavior at various levels of abstraction. For example, a series of simple observations, such as a person's location in a room, can be interpreted to determine more complex information, such as in what task or activity the person is performing. Two kinds of hierarchical Markov models are the hierarchical hidden Markov model and the abstract hidden Markov model. Both have been used for behavior recognition, and certain conditional independence properties between different levels of abstraction in the model allow for faster learning and inferences. And what about the tolerant Markov model? A tolerant Markov model is a probabilistic algorithm Markov chain model. It assigns the probabilities according to a conditioning context that considers the last symbol from the sequence to occur as the most probable instead of the true occurring symbol. A TMM can model three different natures: substitutions, additions, or deletions. Successful applications have been efficiently implemented in DNA sequences compression. And what about the Markov chain forecasting model? Markov chains have been used as a forecasting methods for several topics, for example, price trends, wind power, and solar irradiance. The Markov chain forecasting models utilize a variety of different settings, from discretizing the time series to hidden Markov models combined with wavelets and Markov chain's mixture distribution model. And now I want to talk about hidden Markov model. A hidden Markov model is a Markov model in which the observations are dependent on a latent or hidden Markov process offered to as X. An HMM requires that there be an observable process Y whose outcomes depend on the outcomes of X in a known way. Since X cannot be observed directly, the goal is to learn about the state of X by observing Y. By definition of being a Markov model, an HMM has an additional requirement that the outcome of Y at time t is equal to t0 must be influenced exclusively by the outcome of X at t is equal to x0, and that the outcomes of X and Y at the t is less than t0 must be conditionally independent of Y at t is equal to t0, given X at the time of t is equal to t0. Estimation of the parameters in an HMM can be performed using maximum likelihood estimation. For linear chain HMMs, the Baum-Welch algorithm can be used to estimate parameters. Hidden Markov models are known for their application for thermodynamics, statistical mechanics, physics, chemistry, economics, finance, signal processing, information theory, pattern recognition such as speech recognition, handwriting recognition, gesture recognition, part of speech tagging, musical score following, and partial discharge and bioinformatics. The Viterbi algorithm is a dynamic programming algorithm that finds the most likely sequence of hidden events that would explain a sequence of observed events. The result of the algorithm is often called the Viterbi path. It is most commonly used with hidden Markov models. For example, if a doctor observes a patient's symptoms over several days, the observed events, the Viterbi algorithm could determine the most probable sequence of underlying health conditions, the hidden events that cause those symptoms. The algorithm has found universal application in decoding the convolutional codes used in both CDMA and GSM, digital cellular dial-up modems, and satellite deep space communication, and 802.11 wireless LANs. It is also commonly used in speech recognition, speech synthesis, diarization, keyword spotting, computational linguistics, and bioinformatics. For instance, in speech-to-text speech recognition, the acoustic signal is the observed sequence, and the string of text is the hidden cause of that signal. The Viterbi algorithm finds the most likely string of text given the acoustic signals. And what about the history of this algorithm? The Viterbi algorithm is named after Henri Viterbi, who proposed it in 1967 as a decoding algorithm for convolutional codes over noisy digital communication links. It has, however, a history of multiple inventions with at least seven independent discoveries, including those by Viterbi, Needleman, and Wunsch, and Wagner and Fischer. It was introduced to natural language processing as a method of part of speech tagging as early as 1987. Viterbi paths and Viterbi algorithm have become standard terms for the application of dynamic programming algorithms to maximization problems involving probabilistic and probabilities. For example, in statistical parsing, a dynamic programming algorithm can be used to discover the signal most likely context-free derivation on parts of a string, which is commonly called the Viterbi parse. Another application is the target tracking, where the track is computed that assigns a maximum likelihood to a sequence of observations. And what about the extensions? A generalization of the Viterbi algorithm, termed the max-sum algorithm or max-product algorithm, can be used to find the most likely assignment of all or some subset of latent variables in a large number of graphical models, for example, Bayesian networks, Markov random fields, and conditional random fields. The latent variables need, in general, to be connected in a way somewhat similar to a hidden Markov model, with a limited number of connections between variables and some type of linear structure among the variables. The general algorithm involves a message passing and is substantially similar to the belief propagation algorithm, which is the generalization of the forward-backward algorithm. With an algorithm called iterative Viterbi decoding, one can find the subsequence of an observation that matches based on average to a given hidden Markov model. This algorithm is proposed by Q.I. Wang, for example, and his colleagues to deal with turbo code. Iterative Viterbi decoding works by iteratively invoking a modified Viterbi algorithm, re-estimating the score for a filler until convergence. An alternative algorithm, the lazy Viterbi algorithm, has been proposed for many applications of practical interest under reasonable noise conditions. The lazy decoder using lazy Viterbi algorithm is much faster than the original Viterbi decoder using Viterbi algorithm. While the original Viterbi algorithm calculates every node in the trees of possible outcomes, the lazy Viterbi algorithm maintains a prioritized list of nodes to evaluate in order, and the number of calculations required is typically fewer and never more than the ordinary Viterbi algorithm for the same result. However, it is not so easy to parallelize in hardware. The output Viterbi algorithm, or SOA, is a variant of the classical Viterbi algorithm. SOA differs from the classical Viterbi algorithm in that it uses a modified pass metric which takes into account the a priori probabilities of the input symbols and produces a soft output indicating the reliability of the decision. The first step in the SOA in the selection of the survivor passing through one unique node at each time instant t. Since each node has two branches converging at it, with one branch being chosen to form a survivor pass and the other being discarded. The difference in the branches matrix or cost between the chosen and discarded branches indicate the amount of error in the choice. This cost is accumulated over the entire sliding window, usually equals at least 5 constraints lengths, to indicate the soft output measure of reliability of the hardware bit decision of the Viterbi algorithm. And you can see that here we are using for exploration. You see the algorithm Viterbi here and initialization and find the info basic information and it's iterative until it converges to the best answer. Thank you so much for watching my tutorial video until the end, and also you can download this Python code from github.com/mahsa script.